metal enclosures for all of the outlets.
Hi guys.
Good morning.
So, can y'all see my screen with the calendar and then the picture of that?
I see split screen.
Okay, today's the 9th and 21st, 3 homework assignments due. 2 of them are very, very short. They are motors, 9-lead 3-phase windings, and troubleshooting homework. So let's look at where those are at. So those are due at 9 a.m. on the 21st. It's a week and a half away. Keep in mind also the 9th of October is the last day of this class. So you need to have all this code homework done, all this homework done. What is this? We got a quiz to take, and we got a lot of material left to do. So from here on out, I think what I'm going to do is every day, whether it's a lecture day or a lab day, Wednesdays and Fridays on your lab days, I'm going to spend a little bit of time talking about stuff, record it, and put it on the drive for everybody to look at. And until we get through all the material, we got troubleshooting, which is very small, motor troubleshooting, and then we'll review 9-lead 3-phase motors. You guys haven't done that homework yet, right? We haven't covered that.
No, it's not available yet.
Okay, so we might have gone over it in 150. We probably did if you had me for 150.
But wiring was part of one of the assignments for 150.
Yeah. Okay.
We took it with John.
Well, anyway, let me make sure those homework assignments are open if you want to look at them or get started. But here they are. Assignments.
Yeah, right now I'm just got the training
homework. Troubleshooting homework. Motors homework. 9-lead 3-phase
Where are we
model.
finding this information at?
Troubleshooting homework. Use the files under course content troubleshooting to complete this homework. Motors homework. Use the files under course content motors to complete this homework.
Okay.
So, course content, troubleshooting, systems troubleshooting, test instruments, motor troubleshooting. For that assignment, you're probably going to use systems troubleshooting.
Oh yeah, that's okay.
One of these deals, okay? And there's going to be a lot of things in here that are like, unless I edited it. Shows you the methods, which we're going to talk about today. But if there's any part where it's like, no, looks like I might have edited it. Anyway, this is what you use for the homework. So I just today want to talk to you about these 4 methods and then do an example or 2 on the trainer behind me. I'm not even going to go through the 6-step stuff. A lot of this stuff is common sense, but it is a sequence that you can use in troubleshooting here and on the job, right? But it's kind of like conduit bending in that you get better and better and better the more you practice. And a lot of students will start tackling the troubleshooting on these trainers. And at first they're kind of like, unless it's an easy fault, they're kind of like, I don't know, I'm not confident. The more you do it, the more confident you get. So the 4 methods. Symptom and cause. Output back. Half split. And shotgun. So what I would recommend you do, and this is how I usually end up approaching real life troubleshooting problems, is symptom cause and output back, or a mixture of the 2. So let's read symptom cause. In this method of troubleshooting, the troubleshooter isolates circuits or components in a system according to whether or not they could cause the symptoms you observe. By first testing only in the areas most likely to cause the known symptoms, the troubleshooter reduces repair time. This method is very fast if you see a symptom for which you know there are only a few causes. This is why it is good to observe the machine's operation carefully before trying to isolate the problem. Symptom and cause. I want to go in and find the ladder diagram. We don't have it on here. Are you kidding me? Are you kidding me?
It's not one of those PowerPoints.
No.
Oh, you're talking about that diagram for pages.
I'll find it. So remember, the first three labs for these are just refamiliarizing yourself with ladder logic and hooking those three different scenarios up. The one I have set up behind me is lab 3, so it will operate kind of like simulating a garage door. I'll pull that ladder up here in a second once I find it. There it is. That's lab 2. That's lab 1. Why are we missing lab 3?
Oops.
Somebody tell me why we're missing lab 3.
It was stolen.
Was it not uploaded?
Oh, that's from 2018. Yeah. These are all modified 2017.
There we go. There we go. This is lab 3. Simulates a garage door. So when the start button is pushed, let me get this over here so we can see the thing behind us. Holy crap.
Yeah.
Let's try 150. It's better. Power circuit up top, forward and reverse contact or motor starter, and then 120 volt control circuit. So what this does is simulates garage door. So nothing's going to happen until we hit one of these push buttons, right? So if we close this, that energizes the forward coil, which closes this, correct? So when this is released and that becomes open, we still have current flowing through the coil, so the sealing contact. So right now we've got current going through this and back, and this and back. Now, symptom and cause. Output back is pretty self-explanatory. That's a good approach to all of these, but symptom is we're going to look at this and say what is supposed to be happening here, and it's not, right? So if you're pushing this button and nothing is happening, right? The coil is not pulling in. What is that telling you? Symptom is This coil is not pulling in. It's not necessarily that the motor's not running, okay? That could be your first symptom, but there could be 100 different things telling you that the motor's not running. It could be any one of these contacts. It could be fuses. That's why it's telling you to isolate the one area of the ladder diagram that could only cause that one problem. So the first thing we can notice is, and this is a hint, is the green light on? And let's say it is. Let's say this is just raining out green lumens everywhere. Okay, this light is on. What does that tell you?
Tells me that
That
there's
coil is
energy flow going through the contact.
Right. That means when you press this button, you're getting 120 volts and you're getting current going through that light. So where does the problem have to be?
Either in the contacts or in the coil.
Contacts? If it's not pulling in,
Well, no, it has to be the coil.
it have to be the coil. The green light is turning on, so you're going to look right here. That narrows it down quite a bit,
Yeah.
right? Let's say that green light is not turning on. Same problem. So what could be causing that?
There could be a lot of stuff there.
Anything basically on this wrong, right? And here is what I will tell you to always do in these labs, whether it's these on this trainer or on what comes after that is the wash tank. It's a more realistic troubleshooting tool that we use. No matter what, at any point in this process, you should know what should have 120 volts difference of potential from that point to 2. So where's wire number 2 on this?
Wire number 2 is the negative.
Yep, it's the neutral.
Yeah.
It's neutral because it's 120 volts and we've referenced it to ground right here. Okay, so all of this is 2. That's all 2, and it should be white on your trainer. So you should know anywhere in this process what should have 120 volts if you put 1 meter lead here on 2, anywhere. 1 meter lead here and 1 meter lead right here. If the disconnect's on, what should I have here?
Should have 120.
Should have 120. What should I have here as it sits?
Normally that means you shouldn't read anything.
Nothing. What should I have here?
120.
120. What should I have here?
120.
120. Now let's say I'm pushing this closed because the problem in this scenario is that this is not pulling in. So I'm pushing this closed. What should I have here
120.
and here?
120.
All right, here's where we bring in the output back. So let's read what that has to say. Output back method. In this method of troubleshooting, the troubleshooter starts testing the outputs of a system, outputs, and then systematically works back towards the inputs of the system until the cause of the problem is isolated. This is probably what I would recommend you do most often. The output back method of troubleshooting is very effective in ladder logic circuits. It is usually a slower method, but is a sure method that will lead you to the problem. And I'm not even sure I agree with it as a slower method. It's very methodical, but you can't screw it up if you know what should have difference of potential on it and what shouldn't. Okay, and go back to this. So output back. What is our output in this situation?
Line 2.
Line
All the way
2.
back to the motor.
What is our output or load? What's our load that's not happening? The same as our symptom.
Oh, is it
It was
the green light
the
not
coil,
coming on?
wasn't it?
It's the coil. You could say it's the light too, but really we're more concerned with the motor's not turning on because that coil's not pulling in, right? We need, in order for that motor to start running, we need these 3 contacts to close, right? and that's controlled by this. So if this is your output and we're working back, what's the first thing we should check?
Limit switch.
Nope.
They'll stop, but
Is there still a chance that this forward coil is bad?
there's a chance. Yeah.
There's a chance. There's a chance that the forward coil is bad and the green light is out. Okay, but we definitely want to see, do we have 120 volts right here at the forward coil?
He's going to stop. You go to stop button.
Huh?
You want to check. You want to check from the
Output back. The reason is if you say, maybe the stop button's not working. You check the stop button. Or if you start here and you start working yourself this way, maybe you'll find the problem, but you're going to end up scattering all these different directions that
You
won't.
start with,
Right.
with the,
That's why it's output back, not back output. Okay, so we want to see if we got 120 volts to 2 on this trainer. So where's that at?
Do the load side of the limit
Look at that, it simulated it on the first try.
switch.
Okay, PV1, motor's not starting. This is not pulling in. You can see the reverse. When I hit that, the reverse side is pulling in. So if we're doing output back, the first thing I need to do is check what to 2. What's your ladder diagram? Where am I checking?
checking. Other, like she said, the other side of the.
Line side of the coil. Checking it right now, the way it sits, would I expect to see anything, even if the coil was good?
No, we got fish with it.
Very good. That's something else you got to keep in mind. So I'm gonna, how can I do this? I do. So I'm gonna plug the. Can you by chance read this? Read what my meter is saying?
No. Barely.
At least a little bit. Maybe, hopefully, you can at least see what we're doing here. So I just put a negative or neutral in here. So I'm checking everything to 2, basically, right? So here's a 2. I just found a random 2. Okay, it's all in the same potential, so it shouldn't matter where I'm reading it from. Okay, so the problem is this is not pulling in. So the first place I'm going to look on your ladder diagram is the line side of the coil, which is right here. Forward coil of the reversing contactor right here. When I press that button, I'm getting 120 volts. Nope, obviously. Where's the next place I'm looking? We're working back now. The load side of the limit switch. That's this one. Press the button, nothing. What if I was getting voltage here?
We're getting voltage there.
Tell me.
You have a bad coil.
No, so I don't. I have no voltage here, and I have 120 here.
You have a bad coil.
No, because I'm not getting voltage to it. How's that coil going to do its job if I got 0 volts at it?
So does that mean
Short
you have a
to
short,
LED.
open?
Yep, if I have 120 volts potential here and none here, that means that this wire is broken somewhere. So I got a bad wire in there. But that's not the case. This trainer will simulate bad parts, not broken wires. You hear me? It's pretty important. Bad parts. Okay. So I've got nothing, nothing, and where's the next place I'm looking?
The line side of the limit
The line side of the limit switch, which is, I've got it on the common right here, but anything?
Nope.
Nope. What's the next place I'm looking?
Load side, that reverse contact, normally closed.
What's that called? Normally closed contact for reverse. Why am I running this in series with the forward coil?
Because it's a, oh gosh.
Starts with an I and rhymes with Schminterlock.
Interlock.
Interlock. So the whole point of that is we don't ever want the forward coil energizing while this is on, right? So we put this in there that if this is on, this opens up, right? But you're right, that's where we need to look next. So the load side of that here, push the button, nothing. Line side of that, I'm assuming you want to do next?
Yeah.
Load side of that, line side,
Oh, the voltage.
voltage. What does that tell you?
Yeah, man, charging.
It tells you that this is bad, right here. So how can we verify that? And I will ask you to do this, but to double, triple check that is the problem. I mean, obviously if we got 120 volts here and nothing here, how can we check to make sure that interlock is closed? Or if it's working?
Put it in reverse. Yeah, check the voltage.
No. Remember in the word in one of those methods was isolate? You always want to isolate. So on this contactor, that is pin 2122, which is here and here. Okay, so I would check continuity on there. It's normally closed, so it should always have continuity, right? Unless the coil's pulled in. Correct?
Sure.
Yeah.
So I'm going to turn it off. Disconnect's off. You can't see me on the screen doing that, but the disconnect is off, so it's dead. Take the wires out. So I'm isolating just this part. Correct?
Mm-hmm.
All right. Now I'm going to check continuity across there by going to deeps. So if this is normally closed, I should hear that, right? I'm gonna check both sides of that. I've got nothing. So we're right. There's a bad interlock contact. That is output back. On the same token, if we had 0 volts on the line side of that, we would just keep working back towards the source, right? The next thing we could check is this push button. Was it held down? So basically that's your systematic method is output back. We checked here, we checked here, we checked here, we checked here, and all of a sudden we had 120 volts here, which means that all this stuff is good. We isolated this one component, found out that it had no continuity across it with it isolated, so we know it's a bad contact. 10-4. That's one example of just how to approach this in general. Use that method when you guys are working through all of your troubleshooting stuff. Now, before I cut you loose, I want to show you the last 2 methods that I hope I don't see you using. Go back to this. Half split, which is useful, but not for this kind of stuff. Half split means we take the entire ladder diagram and cut it in half. And you can see on this picture, that's what they're doing, right? The problem here is what?
1.5.
I don't know what they're showing. Oh, symptom, motor coil is not on. So I guess if you're looking at this and saying, well, this has to energize before this closes, this has to do that before this, So I'm going to cut it in half and save some time. Well, maybe.
But then
Might be
you gotta
helpful.
keep capping and half.
Right, right. And that is useful for some situations. I wouldn't recommend you do it here. I would say start there and work yourself back. We know that this TR1 contact needs to close in order for that to energize. So are we getting 120 volts? No. Why not? Okay, where's TR1? Right here. Okay, check that for voltage. Okay, what's that being controlled by? Okay, here. That's not getting voltage. So we check here, right? And work your way back. That's what I would recommend you do for these. Where this is useful though is pull the magic thing up. Here's where this is useful. I would recommend you use this method for like a lighting circuit. And I use this a lot in like outdoor lighting. But outdoor lighting, like especially on a highway, or this could be anywhere, it could be in this room. You've got 15 lights in here. And let's say they were all on one switch, which means you've got light here, 2, 3, 4, 5, 6, 7, 8. You can imagine up to 15, right? But let's say this is outdoors and these are 300 feet apart. And let's say that these are not working. Oh, let me say that. No, I'm not going to say that.
Okay, that's not working. Don't you just try to change the volts and then working backwards?
Well, I don't know. Do you have voltage at this pole? You're just going to take a bucket truck and go
No, you didn't check the voltage.
do a lane closure on the road and go up there and change the lamp? Might want to stop and see if you even have voltage there first, right? Because if you got 2 in a row out, there could be a chance that maybe you got bad underground right here, right? But these are connected in parallel, so on and so forth. So let's say this circuit, photo eye closes at night and it's supposed to energize a contactor coil that turns all these lights on. Okay, and here's the neutral. I'm not going to connect the dots, but let's say that circuit breaker, I don't remember the symbol for a breaker, so I'm just going to put a fuse. Every time it turns on, you blow the fuse. Uh-oh. Uh-oh. What do you do? What do you do? Something here is grounded. Let me tell you what you do. Cut this thing in half, right? Turn this thing back on and see if you trip the breaker. If you do, you know the problem is in this half. You've just cut the whole field in half, right? If you don't trip the breaker, you know that that the problem is in this half. Okay, so then what do? You cut it in half again, just like Brenna was saying. Okay, so we just tested it, and this is still good. Okay, so what we're going to do is cut it in half, let's say here. So we're going to open this up at this pole or at this light, and we're going to reconnect this. Turn it on, see if you trip the breaker. Let's say no, we didn't trip the breaker there. Now you've narrowed it down to 2 lights. Problem's got to be in. You see how quickly you can narrow it down and isolate where the problem is. That's the half split method. 10-4, so it has its uses, not so much in what we're doing. Last method. If I see you doing this, I'm going home. But I do see it a lot. And nothing bothers me more than if I'm working with somebody trying to troubleshoot something and they start doing this. I'll get back. There we go. The shotgun method.
That's what I was.
In the shotgun method of troubleshooting, the troubleshooter tests every component or connection in a suspect area. The shotgun method can save time if there are only a few components to test or the problem is intermittent. However, it's usually the worst method to use and will be the slowest if the circuit is large. Why do you think that's a bad idea? Spray and pray. Yeah, that's a good way to. Here's a shotgun method. I see this so often. Well, my motor's not turning on, so let's see. I got nothing there. I got nothing here. Looking and seeing. What I mean, what do you expect to find? Like 1.21 gigawatts somewhere that tells you this is where the problem is? No, it's not symptomatic at all, or not. It's not systematic at all. You're gonna have a hard time figuring out what the problem is if you're not following a ladder diagram and saying this is not working. I need to see why that doesn't have 120 volts on it and work my way back until I find something that does, right? You got 120 volts here, but not here. The problem is in between there, correct? Okay, so that is my spiel on motor troubleshooting methods. We still need to get into 90 three-phase motors. Troubleshooting motors with a megger. We'll do all that one day at a time. So I'm going to send out an announcement that the people who did not catch this will be able to look at it on YouTube. And just remember, you got those homework assignments are due on the 21st.
Week from Monday.
Yeah, these 3 homework assignments. You got plenty of time to do them. And I'll just plan on doing a little bit of lecture every day until we have all the material covered. And then if it's a lab day, we'll cut you loose to lab after that. 10-4.
Over out.
All right. Let's stop this recording.